Integer multiplication. We now discuss the different applications of the divide-conquer in which the default quadratic algorithm is improved by means of a different recurrence. The analysis of the faster algorithm will exploit one of the recurrences considered in section 5.2, in which more than two recursive calls are spawned at each level. The problem we consider is an extremely basic one, the multiplication of two integers. In a sense, this problem is so basic that one may not initially think of it, even as an algorithmic question. But in fact, elementary schoolers are taught a concrete and quite efficient algorithm to multiply two n-digit numbers x and y. You first compute a partial product by multiplying each digit of y separately by x, and then you add up all the partial products. Counting a single operation on a pair of bits as one primitive step in this computation, it takes big O of n time to compute each partial product and big O of n time to combine it in with the running sum of all partial products so far. Since there are n partial products, this is a total running time of big O of n squared. If you haven't thought about it this much since elementary school, there is something initially striking about the prospect of improving on this algorithm. Aren't all those partial products necessary in some way? But in fact, it is possible to improve on big O of n squared time using a different recursive way of performing the multiplication. Designing the algorithm. The improved algorithm is based on a more clever way to break up the product into partial sums. Let's assume we are in
It
base
doesn't
2.
really matter.
It doesn't
And
really matter.
start by writing
x as x1 times 2 to the n over 2 plus
n
x
over 2
0
plus
in other words,
x2
x1 corresponds to the high order
plus
n
x
over 2
0,
bits, and x0 corresponds to the low order n over 2 bits. Similarly, we write y equals to y1 times 2 to the n over 2 plus y0. Thus, we have x times y equals to x1 times 2 to the n over 2 plus x0 times y1 times 2 to the n over 2 plus y0, which is equals to, if we multiply all those things inside of the braces, that will be x1 times y1 times 2 to the n plus x1 times y0 plus x0 times y1. And let the results of x1 y0 plus x0 y1 times 2 to the n over 2 then plus x0 y0. Equation 5.1 reduces the problem of solving a single n-bit instance multiplying the two n-bit numbers x and y to the problem of solving four n over 2-bit instances, computing the products x1 y1, x1 y0, x0 y1, and x0 y0. So we have a first candidate for a divide-conquer solution. Recursively compute the results for these four n over 2-bit instances and then combine them using equation 5.1. The combining of the solution requires a constant number of additions of big O of n bit numbers, so it takes time big O of n. Thus, the running time t of n is bounded by the recurrence. T of n is less than or equals to 4 times t of n over 2 plus cn. For a constant c. Is this good enough to give us a subquadratic running time? We can work out the answer by observing that this is just the case q equals 4 of the class of recurrences in 5.3. As we saw earlier in the chapter, the solution to this is t of n, which is less than or equals to big O of n to the log base 2 of q, which is equals to big O of n to the square, because q is equals to 4. So in fact, our divide and conquer algorithm with four-way branching was just a complicated way to get back to quadratic time. So it's not good. If we wanted to do better using a strategy that reduces the problem to instances on n over 2 bits, we should try to get away with only 3 recursive calls. This will lead to the case q equals to 3 of 5.3, which we saw had the solution t of n, which is less than or equals to big O of n to the log base 2 of q. If q is equals to 3, there will be big O of n to the 1.59. Recall that our goal is to compute the expression x1 times y1 then times 2 to the n plus the results of x1, y0 plus x0, y1, then times 2 to the n over 2 plus x0 times y0 in equation 5.1. It turns out there is a single trick that lets us determine all of the terms in this expression using just 3 recursive calls. The trick is to consider the results of the single multiplication. That is x1 plus x0 times y1 plus y0, which is equals to x1 y1 plus x1 y0 plus x0 y1 plus x0 y0. This has the 4 products above added together at the cost of a single recursive multiplication. If we now also determine x1 y1 and x0 y0 by recursion, then we get the outermost terms explicitly, and we get the middle term by subtracting x1 y1 and x0 y0 away from the results of the multiplication between x1 plus x0 and y1 plus y0. So thus in full, our algorithm is recursive multiply of xy. First, we write x equals to x1 times 2 to the n over 2 plus x0, which means that we just shifted the first n over 2 bits plus the rest bits, which is represented by x0, and y equals to y1 times 2 to the n over 2 plus y0. First,
then we computed x1 plus x0 and y1 plus y0.
We computed y1
we let
plus
p
y0.
equals to the output
and
of
we let
the
p equals to the recursive multiply of
call
with
x1
inputs
x1 plus
and
x0
y1
y1 plus y0. We let x1
let
y1
x1
equals
y1
to the output of a recursive multiply of the input x1 y1, and we let x0 y0 becomes the output of the recursive multiply of the input x0 y0. Then we return x1 y1 times 2 to the n, because we have already get x1 y1 from the recursive call, plus p minus x1 y1 minus x0 y0 times 2 to the n over 2, because we've already get the p by another recursive call. And we get x1 y1 and x0 y0 from the recursive call. Then the rest term is plus x0 y0, which is also returned by the recursive call. Now we're analyzing the algorithm. We can determine the running time of this algorithm as follows. Given the 2 n-bit numbers, it performs a constant number of additions on big O of n-bit numbers in addition to the 3 recursive calls. Ignoring for now the issue that x1 plus x0 and y1 plus y0 may have n over 2 plus 1 bits rather than just n over 2, which turns out not to affect the asymptotic results. Each of these recursive calls is on an instance of size n over 2. Thus, in place of our 4-way branching recursion, we now have a 3-way branching one with a running time that satisfies t of n, which is less than or equals to 3 times t of n over 2 plus cn for a constant c. This is the case q equals to 3 of 5.3 that we were aiming for. Using the solution to that recurrence from earlier in the chapter, we have 5.13. The running time of recursive multiply on 2 n-bit factors is big O of n to the log base 2 of 3, which is equals to big O of n to the 1.59.